Good afternoon. Any questions? Yes. Quiz question 6. All right, so here it says question 6. So which of the following statements about adding an element is not true? So 3 statements must be true and 1 statement must be false. So do we add the new element at the beginning of the node sequence? Yes or no? I mean, we'll see it in a few minutes. The answer is yes. So one adds elements at the beginning. It's the easy thing to do. Do we check the elements in the bucket to determine if the new element already exists? Yes or no? We have to. It's a set, right? So one of the things in a set is we don't want to have duplicates. And so yes, we do that. If the element matches another element in the bucket referenced by the hash code, add the new element to that bucket. Now this is a confusingly worded statement. So I'm going to parse it the way I want. And I'm going to say, does it match another element? And if it does match another element, which I'm going to interpret to mean if it equals another element, then we're not going to add it. So I'm going to say this one is false. And the last one also is true. To add an element, the compressed hash code must be computed. I don't know where the author of this question got the term compressed hash code, but I think what he means is to reduce modulo the table size. So that's how I took it. Is that the right answer? Does anyone remember? I don't know if I can take the quiz now. Submit quiz. 9 unanswered questions. Unanswered. Correct. Okay. So I guess I was right. Now, this is not the greatest wording ever, right? What does it mean, referenced by the hash code and all of that? But that's how I took it. Does that clarify it?
Why is it so hard implementation of the
I'm sorry?
Is it hard implementation of a hash table?
What's with our implementation of the hash set? It does the first thing. It inserts at the beginning. It does the second thing. Our implementation. It checks for all the other elements first to see whether the element is present. It certainly doesn't do the third thing because that would be wrong, right? Then the element would be added twice. And it does do the fourth thing. It quote-unquote compresses the hash codes by computing them modulo the table size. So the answer is which of them does it not do, and it does not do 3.
So our implementation of the hash table is using hash sets?
Okay, a hash table and a hash set are one and the same thing. So a hash table is just a generic term for this data structure, and so a hash set is directly implemented by a hash table. A hash map is implemented by a hash table with a twist that I'll come to a little later. So the hash table is just like a linked list. It's a data structure. Does that make sense? All right, other questions? All right, so I'm going to go through this fairly short lecture, and then I'm going to talk about some of that homework that's going to start piling up during the exam week, so that at least you'll have a record of what I want you to do. So before doing that, as you know, there's an exam on Monday. It's going to be pretty much the same as the exam that you had last time. You're going to have to draw a couple of memory diagrams. So those are those diagrams with those boxes and arrows. So one of them is going to be, and all of the problems are related to prior homeworks. So would be a super good idea for you to look at all of the homework assignments again and look at your solutions, look at my solutions. Everyone of them, in fact, is going to say, no, I don't know if everyone. But basically they're going to say, here is my solution to homework so-and-so. It might be, here is my solution to homework so-and-so with a bug introduced. And so, yeah, be familiar with the basic setups of the homeworks. You know, those rings, those iterators, whatever we had. It would also be a good idea to have another look at the first exam and see, we're not going to do anything with input and output, of course. We're not going to be doing anything, well, there might be an exception or two, but there's not going to be anything specific about that. But, some algorithm pseudocode, that's all fair game. Be familiar with the rules for writing up pseudocode. So you will be asked to write up pseudocode that follows those rules. So if you write up some random storytelling pseudocode, you're not going to get much credit for it. So be familiar with the syntax that was required for you in that lab about pseudocode, and that I've been asking you in general to follow. Yes?
Are we going to use GitHub?
You're not going to use GitHub. Sadly not. So you don't have to do anything about GitHub. Yes? I don't know. I mean, it's a general technique. So anything that has to do with like the general tools that you're by now expected to be comfortable with, such as the terminal window, command line arguments, unit testing, all of that stuff. That's all fair game. So I don't. I'm hoping that you by now know the stuff and you don't specifically have to practice it. So as far as I remember, there's one thing where you definitely need to run a unit test, for example. And so in Eclipse. The Eclipse debugger will be prominently featured. You just all had a fun lab about debugging linked lists, right? Greatest stuff ever. And so, yes, so there will be something there. So I will be taking a homework assignment, one of my solutions. I will break it in some unpleasant way, and then I will give you some piece of code, and then I will say, run the debugger until this point, and then draw the memory diagram. So read off the magic object numbers from the debugger, put them in the right places, put every arrow in the right place. And then you get 1 point per correctly placed arrow. And then I'll say, and now run it for a few steps, and how did the arrows change? And so that's, if you had trouble with that lab, that would be a really good thing to do again. So I've gotten relatively few questions about all of this linked lists and rings and iterators and all of that. So, I'm naively working on the assumption that you all find this crystal clear. If not, come up with more questions in today's lecture so that impression gets destroyed. But it's all going to be about linked data structures, big O, pseudocode, that kind of stuff. So yeah, of course you're going to have to just remember what the big O of like everything inside is, right? That's like 4 or 5 tables, and so you have to be able to remember that and to apply it to reasonable situations. So that's what it is: linked data structures, big O, pseudocode.
Question.
Yeah.
So I forgot the format. Is it within notes?
So it's going to be the same thing as last time. That exactly how did I word it? So you can whatever you have naturally on your laptop is fine.
Okay.
So you can bring your textbook and you can write things into your textbook, but you can't bring like stacks and stacks of notes or other books.
Well, what if I put stacks and stacks of notes on my laptop?
That's fine. So, yes, that's fine.
Okay, so if I were to realistically write pseudocode solutions to everything you've done on the homework solution, I can just copy that verbatim.
So your strategy is you're going to go through every homework solution
And write pseudocode.
and you're going to write pseudocode for every one of them.
Exactly.
Yeah, you could, after that, doing that, you could actually delete what you have done, and at that point you would have written so much pseudocode that surely you could write any pseudocode ever known to man. So that would not be a bad exercise. Yeah, so, yeah, if that's what you wanted to do, you could certainly do that. Yes? What? There will not be a practice exam. So the reason for the practice exam last time was so that you all know the drill. Oh, someone asked, do you have to use the command line? So the exam will be distributed in the same way as last time. So I will give it to you in encrypted form on Sunday, and on Monday you have to decrypt it. You know how you do that decryption? If last time you were able to do it from Windows or from the Mac, that's fine. There were several people who said, you know, I don't know how to do that, and all I then can help with is Linux. So at the very least, make sure that you know that your virtual machine is in good order and that part works. Or you could practice how to do it your way if you don't like my way. So, but it's so there's no more practice needed really because you've gone through that step. You're going to get this encrypted thing. You download it onto your computer on Monday morning or Sunday night or whatever. So even if the network completely fails, you can work on your thing, and then you could always turn it in on USB stick like last time. So again, bring in a USB stick. Some of you needed it last time, and same thing. Bring in some paper, bring in a pencil. I would strongly advise that you not just bring a pencil, but also that magic tool, the eraser. Because as you know, it's very easy to be in need of one when you draw these diagrams. Yes? Yes. Yes. So it'll be from everything from after the first exam. So the first exam ends was when? So everything from lecture 10 on is fair game. So that's 11 lectures. That's actually quite a few. Now, yeah, so that started with sorting. So absolutely. And now in terms of what you should prepare, there will not be a question that says, tell me what selection sort is, because of course you can bring your book and you can tell me what selection sort is. So what would be more likely is that there might be a question that assumes that you understand merge sort and can use merging in some other context. That might be a good question. Well, I might give you a problem where you have to be able to adapt the implementation, where you have to have an understanding of what it does, and then if the circumstances are somewhat different, then you might have to do the merging that way. That would be a fair question. So I'm not sure that particular question is going to happen, but a question like that. Yes?
So we talking about a Venn diagram?
Yeah?
We're talking about like drawing out the weaknesses?
Yes. Or the ring, or something with an iterator, or like the hash tables that we're doing. Well, actually, no. What we're doing today is not on the exam. So you can be assured there's no hash table. Yes?
Is there going to be around 7 questions again?
I don't know. But, they have parts A, B, and C, and so. It'll again be so that some of you will say, I can't possibly do all of them, and then work the problems in an order that maximizes your score. Not every one of you will get an A, and so if you feel you're one of those who won't, just go through the problems in such a way that you harvest the most points. So read through the entire exam first, and then just work away, you know, as you're comfortable. Just like last time, there's limited opportunity for partial credit, so you're better off, you know, trying to get some problems to work completely rather than dashing off a few random sentences here and there. I know that other professors grade differently because I always get, you know, some students who madly try to fill in a little bit into every single problem. But if there's nothing there of any value, then all I can say is nothing of value, 0 points. And so you have to get to some critical mass of some minimally rewardable item. And if it doesn't rise to that, just skip the problem and work on something else. As you've seen last time, you know, you can get a reasonable grade with answering, you know, far from all of the questions. So the single best practice is, you know, to do some of these activities. Solve another coding problem that has to do with linked lists. Draw a bunch of memory diagrams, write some pseudocode, figure out the efficiency of some algorithms. What I can do, if someone bugs me about it, is I can pick up a few sample questions from the textbook that are, you know, similar to what would be on the exam. And I should have done that. I just didn't have the time. So someone put a query on Piazza, and I will do that. That way you have kind of a semi-practice exam or something that guides you in studying. So you have all week to do this, so don't blow it off. If you had no trouble in the homework, I guarantee you'll have no trouble in the exams either. But if you were struggling with the homework, then, you know, more coding can only help. All right, so let's see what we want to do for today, and then I'll talk a little bit more about the homework that's going to pile up. So you've read through sections 16.4. So you're seeing here that what we're doing is provide a particular implementation of sets with hashing. And so someone asks, what's the difference between a hash set and a hash table? So the hash table really is the same thing as a hash set. It's the more classic term. So a hash table means that we're inserting and removing and finding elements in this particular fashion, so that insert, find, and remove are fast. Order doesn't matter. Duplicates are thrown out, so that's what makes it a set. And so the basic idea is to put objects in an array in a way that they're easy to find. So here I have some array. And so the idea is you take your object, now I'll just write here as a blob, and you cook up some number from it. In a way that cooking up that number is fast. And, you know, let's say this object here gave us 1729, and then you say you put it into that slot. So then we're going to put it right into the slot with the same index. Now, if then a second copy of that object comes along, then we compute its number again, and we look at the same slot, and we say, hey, it's already there. Now, this strategy would work if the number that we derive from each object was totally unique. If we would never have another object whose ID, so to speak, is 1729. And there are some situations in which that happens. For example, if you have a bunch of employees, you'll never have two employees with the same employee ID. So the employee ID would make a fine hash code. You know, the hash code is this unique number that's derived from every object. So sometimes naturally this uniqueness happens. But in many other situations, like when you when you want to collect arbitrary strings, for example, could you turn every string into a unique number? Could you come up with a scheme so that no two strings have the same number? You think it's possible, or is it just plainly impossible? Who thinks it's possible? All right, so a few people. Who thinks it's impossible? Okay, a few more people think it's impossible, and everyone else doesn't want to raise their hand. So it actually is possible, but it's not practical. So let's say that I had the string hello. And let's say for simplicity, we're just using, looking at this with good old ASCII code. It works the same with Unicode, but it's easier to understand with ASCII code. So in ASCII code, every character is really a number between 0 and 255. So each of those would be a number from 0 to 255. And so now you could look at the string as a number in base 256. So it would be whatever the code for O is, plus 256 times the code for L, plus 65,536 times the code for the other L, plus whatever 2 to the 24 times the code for E, and so on. So, but then these hash codes would get very large. They would overflow integers for sure. And if the string is long, you would need arbitrary precision numbers. It would be very, very tedious to do. And it would also be useless because your array that holds them can't be larger than 4 billion or so anyway. I think 4 billion is the maximum size of an array in Java. So yes, you could assign a unique number to every string, but it wouldn't be very practical. So you're much better off saying, you know, fine, sometimes these numbers, and most of the times they're going to be different, but sometimes you might have a collision. And so we'll just deal with collisions. And that also solves the second issue that you have, namely that the array has to have some finite size. You can't set up a 4 billion sized array for every lousy hash set that you want. So you should start out with, you know, some smaller number for the array, some smaller size for the array. And so then, of course, you have to somehow compact down your hash sets, or your hash codes, and collisions are more likely. So there are two things we want to do. Is number one, we have to somehow live with collisions, and number two, we have to live with arrays that are not incredibly huge. And those two things are related, and they're not really hard to deal with. So and we'll hold that thought for a minute and look a little bit more about how these hash functions work. So now, to compute these hash functions, we have to somehow find a way of crunching down any old object into an integer. So let's just look at an example. So remember that quiz class that we had at the very beginning of the semester? A quiz had a title and an array list of questions. Right? Now imagine, visualize a quiz object. It has a title, quiz 15, and it has 10 questions. Now turn it into an integer. The integer has to depend, of course, on the title and the questions. If you have two different quizzes, those integers should hopefully be different. How do you do it? And of course, when the same quiz, the exact same quiz, same title, same set of questions, is seen another time, then it should be the same number. So you can't just pick a random number. So if you had a hash code that was a random number, that wouldn't work at all, because when you see the same thing twice, you wouldn't get it twice. So it's not obvious on how one can do that reduction. One thing you could, of course, do is you could always return 0. That would work. That way, when you see the same quiz twice, it would be the same answer. But it wouldn't be very efficient, because when you see different quizzes, they would all map to the same thing, and so that wouldn't be good. So you have to somehow figure out how to scramble them in a methodical way. So that's what we want to learn. So it's good to see how that works with strings. So this is the code that I copied almost verbatim from the implementation of Java Lang string on how they compute a hash code. So there is So clearly when you have a string, you somehow want to use the character codes of the string in some way. Those are integers, and you want to combine those integer values to a larger integer value. And so the most obvious way would be you would take a string, you say, let's just add up the character codes. That would scramble them pretty well, actually. Right? So if you have like hello, then that would be a very different sum of character codes than if you had goodbye. And there's only one reason that they don't do it like that, and that is, let's say we did it like that. We say the hash code of hello, or the hash code of any string, is the sum of the character codes inside it. Now, can you tell me another string that has the same hash code as hello?
Anything that has the same, like another permutation?
Very good, right? Like Holly, right? And so it would be very easy to come up with collisions that way. And those permutations, are not that rare in real life. So in order to overcome that issue, they're doing it slightly different. They're taking a character code, and so in this case, we're starting at the beginning, so that would be the character code of H. And then we take that thing, multiply it with 31, and then add to that the character code for E. Then we multiply the whole thing with 31 and add to that the character code for L. Multiply the whole thing by 31, add to that another L. The whole thing once more times 31, and add the character code for O. And it's going to be some number. Now if we were to switch the letters, we would almost certainly get a different number. Maybe by crazy random chance it would be the same number, but it sounds very unlikely. And it's completely deterministic. If we see hello again, and we make the same computation again, we get the same crazy number again. So it seems to fulfill our two conditions that we had for hash codes, that the hash code needs to depend on the object contents. Same contents gives the same hash code. And it should spread around different objects somewhat. And it does seem to spread them around. As we can see, I'll just give you some hash codes. The hash code is Fred is this unlikely looking number. This is the hash code of Barney, and it looks completely different. So I can generate hash codes of different. Why is it negative? Why does poor Sarah Linda have a negative hash code? All I've done is I took a character code, multiplied by 31, added another one, multiplied by 31, added another one, multiplied by 31. How can I get negative? Can you have negative character codes? Like the cat with heart-shaped eyes, does it have a negative character code? Yeah. Overflow, exactly. At some point, this thing has gotten so large that it overflowed to the largest possible integer, and then it wrapped around to some negative integer. Does it matter for hashing? No. As long as it's likely to be different from other hash codes, and as long as it's the same if I call it twice, which it is, then that's fine. So the negative numbers they can perfectly well arise, but they're nothing to worry about. All right, so now you get to try it. You get to compute a couple of hash codes. So I wanted you to tell me what's the hash code of the string cab, C-A-B. So if you learn nothing else in this course, you should remember that lowercase d has Unicode value 100. It's easy to remember because lowercase d is the same thing as the new line squared. Did you know that? So if lowercase d is 100, what is lowercase c? Slow day today. What's lowercase c? What's the Unicode value of lowercase c? Thank you. 99. That's how to never experience this. All right. So, and then A is 97 and B is 98, right? All right. So work with that.
I have a question.
Yeah.
So the negative numbers don't matter because when you're trying to get an index for an array, it's when you're going to compress that negative number?
Exactly. So if you looked at the code, there's a line that says if h is less than 0, h is minus h. Now you have to be a little bit careful to do that before you compute mod the table size, because a negative number mod something is still negative. All right, so it is 99, and now let's see, so to that, let's see, we multiply that by 31 plus 97, the whole thing times 31 plus 98. So good thing Emacs has a calculator. Um, 97, 31, 98 plus 9H244. All right, so let's see who got that. All right, so most people have fired up the Emacs calculator and gotten the same thing. Yeah, so if you ever lost on a desert island with nothing but Emacs, so it's MetaX Calc, and then you get, interestingly enough, a reverse Polish calculator with a stack. Here it is, so 98,244. So that's the hash code, and it's just what it is. Of course, the simple way to do it is to just fire up JShell and to ask JShell and here it is. Okay, so we figure out the genuine hash code of this string. Now, if you have something else, like here we have a country class, and a country has a name and an area, and then our task is to combine those in some way. And so the easiest way to do that is to say make a hash code out of each field. So we're calling the hash code for the string. Now to get the hash code of a floating point number, you have to first make it into an object, and then you compute its hash code, and then you multiply them the exact same way. The first one times 31 plus the second one. There's no magic to 31. You could use any other number. You know that there's some superstition that says a prime number works better, but I don't think it's actually true. So in any old number that scrambles these, 31 is just the traditional choice. You know, the number of days in January or something. So you scramble them in some way. Really doesn't matter how you scramble them, and there you have a hash code. So every once in a while you do have to do that and implement your own hash function. Now, if if one were very lucky and one had very large arrays, one would never have to worry about collisions, of course. But in real life, it's going to happen once in a while that there are collisions. They're not all that common. Remember when you had a few weeks ago that assignment where you had to find two strings that had the same hash code? And one went through the entire dictionary, and there was what, like UG and 7 had the same hash code, and otherwise thousands and thousands of things, they all had different hash codes. So it's not super common. Of course, once you reduce modulo a small table size, it's going to be more common that you have collisions. And so we have to do something with collisions. So in the olden days, before people understood linked lists, they did something that was pretty cumbersome. They would say, okay, if you had an element here that was already there, and another one with the same hash code came in, then they would put it into the next field. And then the next one into the next field over. But of course, that scheme got you in trouble once there was already a cell occupied before. You know, if you had another one here that was already there, you know, then what do you do? And so for a while, the literature was full with crazy schemes on how to deal with these problems. And so there's a couple of exercises that I will mercifully not assign to you in the book that make you go through that kind of thing. And so generally, these days, I don't see anyone doing that. So we're going to be doing something that is conceptually a much simpler idea. We're going to say, we're not going to store those values directly in the table. Instead, we're going to store for each hash code a list of all of the values with that hash code. So each of these things is a list. And in the interest of space, you know, I'm not drawing all of the list elements here. Like that. So each, when you look at a particular list like this, these all have the same, I can't read that. Or at least the same compacted hash code. And this thing is called a bucket. Different buckets then have different hash codes. Some buckets might be empty. The order of the bucket makes no difference, because the order of a set makes no difference. So we're free to reorganize or to put things anywhere where it's convenient for us. So that's the big idea here. And it's pretty simple. Here I have an actual hash table, and I don't remember what its size was, like 101 or something. And so this is actually accurate. If you compute the hash codes of Juliet and Catherine and Tony, they're all reduced to 79 mod something. So you compute the object as the index of an object, and so here you have to take the absolute value of the hash code so that you don't worry about negatives. You mod it by the table size, so now you have something that's between 0 and the table size. And you deal with collisions very simply by having a bucket that holds all of the values with the same hash code. Now one would hope that most of these chains here, most of these buckets have size 1. Or maybe there's a few buckets that have size 2. If one of those buckets is very long, that would be bad. That could happen, of course, either by bad luck, or much more likely, if someone chose a bad hash function. In the worst case, if the hash function returns always 0, then your hash table has every single element in the 0 bucket in a long linked list. And that would be a very poorly performing hash table indeed. It could happen if that's the hash function that you chose, but in practice people don't do that. Now, the third alternative that I've read once about is that there was someone who actually attacked a computer program by purposefully feeding in large numbers of strings that all had the same hash code. And so the attack was to slow down the computer program somehow. And so it ran on the web somewhere, and so you could feed in inputs. And so that person figured out millions and millions of strings that all had the same hash code, random gibberish strings, not strings in the dictionary, and thereby managed to slow the program down to a crawl. And so that is a viable attack on a hash table, I suppose. Not a very common one. All right, now let's see how one does the common operations on a hash table. How do you find whether an element is already present? Remember, there's three operations that we want to be able to do: find, add, and remove. I'm starting with find because we'll use find and add and remove. So let's say we have our table here, and now we have a name such as Fred. And as it happens, Fred's hash code reduced modulo to the table size is 65. So that means if Fred is present, he's going to be present in the bucket that you see here. There's no way that Fred could be here because those are all of the ones whose hash code is 79, and we only care about 65. So then at this point you do something completely obvious. You look at the first element and see, is that Fred? No. The second element, that's Fred? No. We have the end of the list, so Fred is not in there, and we return false. But now let's say we're looking for Harry. Harry's hash code is 65, and you do exactly the same thing. You look here and you see, is it Sue? No. Is it Harry? Yes. And so one returns true. So the algorithm means compute the hash code. Visit all the elements in the bucket. Check each of them. Are they the desired element? And if you found it, you return yes. If you found no match and you reach the end, you return no. What's the efficiency of that? Computing the hash code. Now, we have to make some assumptions here. In theory, computing the hash code could take forever. Someone could come up with a hash code computation that has a near infinite loop in there just for being annoying. But in practice, that would be a bad hash function. So there is another requirement for a hash function, that it be reasonably fast and that be independent of anything. That it should not depend on the size of the set that we're trying to form. So we're always assuming that a hash function is over after some reasonably short number of instructions, that the hash computation is O of 1. So yeah, if you had a situation where that wasn't the case, then all of these bets would be off. But that's an underlying assumption that computing the hash code is O of 1. Reducing it mod the table size is, of course, instantaneous. So we can find our bucket in constant time. And the other assumption that we're going to make is that life is good and that all of the buckets are short. That it's always going to be the case that, say, that there's some constant upper bound on the size of the buckets. Now, like I said, one could have a terrible hash function that only returns 0 and 1, or only returns 0, or only returns values between 0 and 9, and that would be bad. But with a normal run-of-the-mill hash function, that doesn't happen, and it is, in fact, in practical applications the case. All the buckets have more or less the same length, and as long as the hash table doesn't get too full, then you can assume that, let's say the table size is 1,000 for the sake of the argument, and have 5,000 elements in it. Then in practice, it is true that the average bucket has length 5. And so that's independent, semi-independent of the size. What happens if you have 1,000 table entries, meaning 1,000 buckets, and now you put 1,000,000 elements in there? Then, of course, each of them would be 1,000 in average, and the answer would be you wouldn't do that. Every hash table implementation will rehash, will grow the buckets list when it gets too full. So that's something called a load factor. The standard load factor is not even an average size of 1. The standard load factor is as soon as 75% of the buckets are occupied, then one rehashes. One makes it twice as large and moves all of the elements into their new position. And with that, one can make the assumption that all buckets are really short. Just 1, 2, 3 elements, maybe. So going through a list of buckets is assumed to be constant time. And with those two big assumptions, computing the hash function is constant time, the length of the buckets is short, then it's clear that looking up an element is also doable in constant time. You get there, you look at 1 or 2, maybe 3 elements, that's the max, and either you found it or you haven't found it, constant time. So find is an O of 1 operation. Now, so that's good. And it's actually a little bit surprising, because how long does it take to find an element in an array? Now, suppose you have an array, a long array of strings, and now you want to find out, is Fred in that array? Oh, it's O of n, right? Because you have to scan the entire array. Can you make it faster? O of 1 is too fast. There's no way you're going to get O of 1 with an array. So if it's sorted, then you can do binary search, and then it's O of log n. So if you have a sorted array, then you can get it to O of log n. And but O of 1 is better than O of log n, right? So O of 1 is really amazingly good. So so the hash table is, you know, made out of humble stuff, but it is really a very efficient data structure. All right, now how about adding an element? And again, it is really easy. So if we look at the picture here, so now we want to add Fred. And again, we're assuming that Fred's hash code is 65. And now, first of all, you start out with the exact same thing as with finding. You try to find Fred, because if it was already in here, then adding would mean you don't do anything, since we don't want duplicates. So we're starting out with finding. If finding says, hey, Fred is already there, we're done. O of 1, because finding was O of 1. If Fred was not in there, then we need to add him. And that means make a node, move this pointer, set this pointer, done. O of 1. Right? It's this constant set number of steps. Make a new node, move a couple of pointers, done. Yeah?
So why couldn't we do duplicates in this implementation and just have a counter for the node?
You could, but we just want to implement a set. Sets are really useful. So, and yes, so I could perfectly well have an exam question that says extend this thing to a bag with counters. But the set is a more fundamental data structure. You can always think of a bag as a map where the keys are the elements and the values are the counts. So if we can do sets and maps, then bags are kind of not that fundamental. So it's just generally that one wants to come up, you know, with the most fundamental data structure first, and then one bases the other ones off it. So could we insert Fred at the end? Why did I insert him at the beginning? Seems unfair that Fred came last. Why does he get put in first?
If that's O of 1 instead of O of n.
No, it still would be O of 1, because the list is assumed to be short. The bucket is assumed to be short. So one could perfectly well put Fred at the end here. You know, what you have to do is you would have to traverse these links, and then you would say, okay, he goes in here. It still would be O of 1. So the assumption is that buckets are so short that you just look at them in an instant. It doesn't depend on the total number of elements in this. So the idea is that the table is large and each bucket is short. But it's just unnecessary work. There's really no great advantage of doing it. I suppose one could do it on the strength that since we're already doing the find implementation, I must have been here, right? Because I was looking at all of them. And so if I cleverly had remembered the predecessor of that thing, then I could have, no, I just didn't remember this thing, right? Yeah, if I had retained this pointer, I could add it at the end. So you could do it either way. That would be a great exam question to make you do it at the end. It's just the implementation, and the book happens to do it at the beginning because the implementor in the book, meaning me, was lazy and first called find. and find return to Boolean, and then the pointer was forgotten. You could do it either way. So there's no magic one way or another. So one of you asked that question about in the quiz question, and I hope that quiz question really says the implementation in the book. There's nothing in the law that says a hash table in general must add things at the beginning. Just my implementation happens to do. So how about remove? And remove is also just as easy, because suppose we want to remove Sue. Well, what do? We compute the hash code. Sue has hash code, reduced mod the table size of 65. So we look through this bucket here and try to find Sue. Here she is, and so we remove her out of the singly linked list. And I think again what I do in the book is I first call find. Do I? I don't even remember. But you could first call find, or you could simply traverse the linked list. And if you find Sue, you unlink her by linking up the neighbors in the correct way. And if you never found Sue, well, then you just return false, and she just was never there. Either way, finding the hash code, constant time, traversing a very short list, constant time, and removal is constant time. Now, it does say here it's O of 1 plus and not O of 1. And the plus comes from because if the hash table fills up, we need to rehash. We need to make a table that's twice as large. Oh, and then what do? It doesn't say here. So here I have my little short hash table. And it's gotten all full. And this means full for a hash table. All of the buckets are occupied, all of them have length 1 or 2. So now I make a table that's twice as large. And what do I do with the elements? So where does the red element go now? Remember, this is always a non-trivial question. We had that same issue with the circular array. To grow the circular array, one couldn't just randomly shovel the elements into the same positions that they were before. Or, we had to think about it. And here it's kind of the same thing. So where's the red element go? Yeah, so I'm at the point that I have a hash table that is overweight. And in the world of hash tables, they don't go on a diet. Instead, they just double in size. It's much better than our world. And but then you have to do something with the elements, right? So now I've gotten a shiny new array, and now I need to move each of the elements into its new home. What we did, and so if I may draw the parallel picture with the queue, we had this last time. So we had a queue. Here was the head. Here was the tail. It was completely full. And then we had a queue that was twice as much. And then what we actually did at the time is we took one batch and put it here, and then the other batch and put it here. But we had to think about how to do it. It wasn't obvious. And that's generally the case. When you grow one of these data structures, you have to think of where the stuff goes. And so I want to go through the same thinking here. So I have to find a new home for every element. And so I'm starting with my favorite, the red one. Where should I put it? Yes.
Could you take another function and apply it to find like an adjacent bucket to the red money?
Okay, what function would I, so you feel the need to apply a function to the red element.
Right.
Which function?
He's saying create another hash function.
Yeah.
Okay, so we're calling the hash function on it, and now it's going to, what's it going to tell me? Over here, the hash function must have said 0. Will it again say 0?
So he's saying put a little, re-implement it so that you tweak it a little bit by one.
No. I guess here's a way on how you can tell what has to happen. Let's say that we have another one of the red ones coming in. So imagine all our work is done, and we now already know what goes on here on the right-hand side. That all of this stuff here, we know what happens. Now another red one comes, and now we want to add it in. Of course, that adding must not succeed because we shouldn't have 2 red ones in there. So what does the algorithm say? That algorithm says you compute the hash code of the red one, you look at whatever bucket that gives you, and there you expect to find the red one. So what we must do is we must put this red one into the correct bucket. And that means we have to do the exact same thing. Compute its hash code without tinkering with it or without adjusting it. Compute its genuine hash code, but now we reduce it modulo the new table size. And then we put it there. So I said before, this hash code was obviously 0 because it ended up in the 0 bucket, but that was actually a lie, like so many things I say. So wasn't 0. The hash code modulo the table size was 0. So here this table had what size 5, so hash code mod 5 was 0. Now we double the table size. Hash code mod 10 could be 0 or it could be 5. We don't know. So we simply have to compute what the hash code is, and then we put it there. There's actually a much simpler way of thinking about it, and that is simply iterate over all the elements in the table and add them all. If you add them all using the regular old algorithm for adding, compute the hash code, find the bucket list, put it to the front of the bucket, then that'll work. And what's the time involved? It's O of n, because it's a constant time operation for each of them. So ever so often, one has this expensive O of n relocation. But if we double the hash, the table size each time, then those expensive relocation happen more and more infrequently, and the same kind of cumbersome logic that we saw with array lists also applies here, and it will be amortized constant time. So there is an expensive operation going on every once in a while. And so I want you to be able to visualize that this hash table gets fuller and fuller, and then this one really expensive step where one doubles the table size, reinserts every single element by recomputing its hash code mod the new table size, and by reassembling all those buckets. So the buckets may look quite different afterwards. It's expensive. It's also, and that's why it's useful to know, because it's a common interview question. Fast forward a little bit where you learn about concurrent programming, so you have multiple threads inserting stuff into a shared hash table. And this really happens if you don't take special action to make sure that only one thread at a time touches that hash table. It is very, very easy to have a situation where one of the threads fills up the hash table to the brim. It then regrows itself, which is an expensive and slow operation. And the other threads, while this is in progress, are trying to insert 20 elements. And complete chaos comes up. It's a beauty to behold. You get exceptions all over the place, and so this is what I usually do when I first teach people about concurrency as a negative example. And it is a common interview question where someone might say, what exactly happens down on the ground when you're in this situation? So that is the expensive case, but it's rare, and so we're justified in putting the plus here. All right. So now I want to raise awareness of an unhappy issue. So here I'm defining an employee object. I have an employee class. And so we want to make a hash table of employee objects. And we're defining an equals method on employees, where we say two employees are the same if they have the same ID number. So there could perfectly well be two Fred Smiths in the organization. So checking the name is not good enough to see whether they're the same. But if the ID numbers are the same, then it's the same Fred Smith. And once the ID number is the same, there's no point in checking for the name or the age or the salary anymore. Right? I mean, if the ID numbers are the same, then that's going to be the same employee. So that seems like a very reasonable test for equality. Two employees are the same when the ID numbers are the same. Now, of course, Fred is dimly aware that somewhere on slide number 2, it says that when you define hash code mumble, mumble, mumble equals mumble, mumble, but he didn't pay attention. So he didn't define hash code at all. Now what happens? So I don't just want to hear it doesn't work. I know it doesn't work because on slide 2 it said equals mumble, mumble, mumble hash code. But I want to know exactly what happens now that you know what goes on inside a hash table. So ponder that and tell me which of these 4 cases, and one of these 4 cases will in fact happen, is going to happen to poor Fred. Yeah.
What is homework 11 solution going to be listed?
Oh, I could do it right now while you're pondering this question. No, I'll do it later tonight. Put something on Piazza to remind me. All right, so here's the employee class here. And so there's no hash code method defined in here. None. So it seems plausible that if you now start inserting employees into a hash table, that the compiler would say, that can't work. A hash table needs hash code. How would the compiler know? It would know if there was some kind of like a hashable interface. You know, there's comparable where you have a compare to method. Is there a hashable interface? Why isn't there a hashable interface? How does the hash table know that there is a hash code method? or whether there is a hash code method.
Objects,
Aha! Every object has a hash code method because java.lang.object defines hash code. So that probably blows out number 1 out of the water, right? There is a hash code method. What does it do? So if I take, where's my JShell here? So if I take object foo equals, give me an object. Java system.out. Right, system.out is an object. What is its hash code? Did you know that the hash code of system.out is 15? Where does that come from? How does it compute a hash code of system.out? I'll just make myself a new class. Okay, and now I have a new A, and I ask, what's its hash code? Oh, that's weird. Why do they have different hash codes? I've made 2 elements of A, 2 instances of A, and then they're exactly identical, right? They both have nothing inside. They have different hash codes, yes?
All the different memory addresses.
That's exactly what it is. Yes, so it depends on the memory address. So the object.hashcode takes the memory address, munges it in some way, and that's where the hash code comes from. So could you get a runtime exception? Not really, because object.hashcode exists. It will be called, and it'll just return whatever value it returns. So it's neither A nor B. So let me see how everyone was doing this. So most people think number 3. So could it happen that we have multiple employee objects with the same ID and we end up with more than one? And so that certainly can happen, and I'll give you a scenario how. So let's say that we had an employee with the ID 1729 happening to be in bucket 54. And he ended up in bucket 54 because by random chance the memory address modulo the table size was 54. Now we get another 1729, same ID. The ID is not used to compute the hash code, of course. The memory address is used. And now what do we know about the memory address here? It could be something different, right? Let's say it's 72, and then the same guy would be in there twice. And so if this was the layoff list, now this employee might be laid off twice, right? So maybe there was something that, there was that duplicates were supposed to be eliminated, and it doesn't work. But it could also happen that by random chance, that if this one was seen a third time, that again it happened to be hashed to 54. And in that case, then the duplicate would be detected, because then the bucket would be scanned. So the bucket is, when the bucket is scanned, it calls equals, and so equals does check the IDs. So it could go either way, depending on your luck. Maybe when the same employee was hashed the second time, they happen to end up in the same bucket, then equals works flawlessly. Or they end up in different buckets, and then equals never had a chance to find the duplicate. So the correct answer really is 3. And so the moral is that whenever you add equals to a method, not to a method, to a class, whenever you add equals to a class, and that's a common thing to do. You often want to compare objects by some criterion. Whenever you add equals to a class, you must also remember this and add a compatible version of hash code. Either you add equals and hash code, or you don't add either. You don't use either one of them. But only having equals and no hash code is bad. Only having hash code and not having equals is also bad. But so either you have both or you don't have All right, so that's, oh, we have more questions. Yes, so let's do it the other way around since we have a few minutes for this. So now, Fred does it the other way around. He makes a hash code, but he doesn't make an equals. And so the question is, what's going to happen? So let me clone this here. So we know it's bad, but what is actually going to be happening with the badness? So now we're hashing the ID. So that means in our picture here, this situation that I've had here could never happen, that that every time that this ID 1729 comes, it always gets mapped to the correct bucket. So the second one here, it definitely, it gets now added to the bucket maybe, or it gets compared with the things in that bucket. That's now for you to find out. So if you don't define equals, do you pick up an equals from somewhere? Just like you picked up a hash code? Oh yes, Java Lang object has an equals method. How does Java Lang object's equals method work? That's very simple. It says, I am only equal to myself, and I'm different from everyone else. So it says if the object references are the same, then it's the same object. Otherwise, they're different. So we don't get a compile time error. We don't get a runtime exception. So now let's see what happens in this case. So we're having the second duplicate object with the same hash code. Now equals will tell us that they are different. Therefore find will tell us that it couldn't find it. And therefore it will absolutely, totally, in every single case, add a duplicate. And the poor fellow is going to get laid off twice. So in this case here, you will always add up with duplicates because equal cannot tell that they are the same. See if our 81 fast voters got this. Indeed, oh, this is great. All right, very good. So this turned out to be longer than I thought it was going to be. You can ponder question 4 on your own. And so prepare for the exam, and I'll see you next Monday. Thanks.